Hi boys and girls, welcome to a new IB Physics video. In this video, we'll focus on chapter 6.2, Gravitation. As usual, we'll look at the study guide from IBO in this chapter. Mainly, I think you can look at the equation required here. When you're doing the question, sometimes the question has not provided the data for you, say for the Earth radius or mass. You may need to find it from the internet yourself. And also the main ideas in this chapter could also be related to the circular motion. That's why they put it in both of them, chapter 6. So you may need sometimes some equations from the circular motion in the previous chapter. Before we start, I would really like to recommend you, I think I've mentioned it before, about the Angry Bird space. So it's not a completely correct physics engine, because if you look at if you play the game before and you see this is like the gravitational field, it's actually not really like this, but I mean there should not be like a limit in the game. But if you try to play the game, you find that if you try to shoot, say here, then you find you actually go in a straight line. However, it should not be true. So but anyway, I think it's still very excellent that people made this game. And if you have time, maybe not on the PC, maybe when you're traveling, then maybe you can download the apps and play it when you are traveling on bus or on a car. First question is very simple. You apply the Newton's law of gravitation with all the figures that you find from the data booklet, or say for the mass, you may need to find it on Google. And after that, you can find out the answers. Second question is very interesting. If you look at diagram A here, what the question said, basically you can interpret this shell as if a lot of particles here. So these particles acting on the middle sphere would have, of course, gravitational force, and they would, all of them would attract the middle mass small m towards each of them equally, since it should be a uniform density here. So in that case, the gravitational force experienced by the middle mass m here would all be cancelled out, because this is a perfect circle here, perfect sphere you may say, and therefore for part A it will be 0. For part B, it also 0 because of the Newton's third law itself. The forces acting on A to B, or to A by B, or to B by A is basically the same. For second part C, it said now you put an extra ball with small m here, and the distance is already shown as 2r, and determine the gravitational force. So what you're going to do here now is the first one should be talking about the mass inside the sphere. So this is part C, asking about you. So it has to be 0 firstly, because of this is due to the shell, and the second part here is due to the new small mass m here. So obviously using the gravitational law, you find this equation and you find answer will be this one. Pay attention to the brackets here, so it will be 4r squared instead of usually people would think, well, mistakes would be 2r squared. So make sure you got a bracket here so that you remember to square the 2 as well. For part D, it asks you about the mass experienced by the one outside the shell. So this time you cannot apply third law, because you can not directly, but you can, but not directly helping you. So simply what you're gonna think is the forces acting on this new mass will have gravitational force from the middle small mass and also the capital M mass here. So for the first one, it would be thinking about the easier one, so the small 2m adding to each other, just like part C. So 4r squared. Basically, I just copy. For the last one is slightly complicated here. So what you're gonna do is, if you think about the last one, of course this is referring to the shell. And how you can know I should do the radius of 2r here is because think about the shell. It's like the I mentioned particles, right? So if you think about one thing that you learn in GCSE, say for a circle, something called center of gravity that you learn in GCSE. That is basically the usually for regular shape like this one, it will be the middle point. Or by definition, it should be the point where when you cut through it, the mass will be the same along two sides. So in this case, what happened in this sphere is this is where the CG is, and you may take the this point as the concentration of the mass here, and therefore this is where you measure the well, basically it's here, measure the distance from, so it will be 2r here, and that's why the answer is like that after you simplify it. Next question is pretty easy. Usually my usual practice, which I like to recommend you, is try to draw the diagram over here. So draw a diagram and put down the information given by the question. And for this one, the ratio of gravitational field strength. So don't get this question wrong. This is talking about when you are on the surface. So let's say there's a person on the surface and the same person on the surface as well. The gravitational field strength that these two people would experience. Not A acting on B or B acting on A, but the one on the surface itself. So what you're gonna do is the R you use will be the radius of the planet itself, and just apply the equation and you should be able to find the answers here. Next question is again similar to the previous one. I will also draw the diagram, even is pretty easy, but anyway, I will always do it. And after that, again you do the ratio thing, substitute the formula, and after that you substitute the number and find out the answers. Here is also another interesting question here. It tells you that this time they have different mass. For A is 27 greater than B, so that's why I put on 27m and one small m for B. And for the density, they will have the same density. That's why I put the rho here. And it asks you to calculate the ratio of 1g over the other g. So what you're gonna do is, of course, you need to know the radius ratio first, because using this information will not be enough to help you. So first of all, you use the density equation, rho equal m over v. And I will write this one because it's what happening here. Density A equal to density B planet. And after that, you apply the equation. I will use VA to represent volume of A, VB to represent volume of B. Try to not skip the step if you are not very familiar with this. And after that, since you know the volume of a sphere is calculated by this equation, if not, at least I think you can at least put down radius cube in that case, and eventually it still give you the same answer if you put down say for similar, I think you learn it in math, similar volume, similar shape, similar volume. In that case, you will find the radius at last will be 3:1 ratio here. So 3RB will be equal to 1RA in this case. After that, you should feel very happy and you can substitute all the things and you should be able to find the answer. Pay attention, the 3 here again is having a bracket, so it will be 27 over 9. The answer is 3. Next question is actually very simple, although it's the same planet, but you may just treat it as like 2 different planets. In that case, original one is M and R. I like to put an O here to represent the original planet, and after that it will become half of the original. So half mass of the original and half radius of the original as well. In that case, I ask you to determine the new one using in terms of the original one. So what you're gonna do is write the original G first using its own value. After that, you use the exploded one, G, and substitute the mass and radius. And after that, you would like to extract these things out because this is basically the same as this, and therefore you can substitute it and take it away and change it to GO in this case. So 2 will be left after you find 1 over 2 over the square of 1 over 2. The answer should be 2, and that is the ratio. Next question is pretty interesting, but it has some problem. It has language cancer, because if you look at the question, you can read that you can't really understand because it asks you to calculate the fraction of the distance from Earth to the Moon, where the G is 0. But what does it mean by the fraction of distance from Earth to Moon then? So I guess what it means is the point, of course, where the G is 0 and the distance between that point to the center of the Earth and the other distance to the center to the Moon. So I guess that is what it is intended to do. So if you do it in the other way, that's fine, as long as you get the idea correct. So basically what you want to do is I define the D1 and D2 here. So that is my aim, to find the ratio of D1 and D2. So by doing that, I need to look at the condition. So condition is G equals 0, and therefore G from the Earth and to the Moon will be equal in that case, since they are on opposite direction, right? And after that, you substitute the things you know with different mass and D1 and D2 over here. And after that, you can eventually figure out the ratio of D1 and D2 is 9. So that means if you want to find a point where you have no G force, you have no gravitational field, that means you have to go for the place where it is near the Moon with 9:1 ratio. Next question, I would say there are two parts. The first part is to calculate the gravitational field strength at P. So in this case, obviously the G that attracted by both two objects will be equal because they have same mass, same distance on both sides. So therefore the G will be 0. In part B, it asks you to state the direction of gravitational field strength at Q. So obviously, it will be attracted straight from the point where Q is to these two objects. And if you are only saying the direction, then of course at last it will be pointing upward. But I guess you can calculate it yourself. If you did not, please pause the video and try to do it now. So if you need to calculate the gravitational field strength at point Q, what you're going to do is, of course, you need to calculate the distance first. So the distance directly is using the Pythagoras theorem, and I try to keep the whole number, so I did not use a decimal to represent. And after that, you can apply the law of gravitation, which at last will give you this number. And if you look at the explanation from the publisher, I think that one should be a mistake. And at last, you can probably think about this is more like force. In that case, you can take the force towards each object and decompose them into a horizontal and vertical component. And of course, these two vertical components at last eventually would cancel out each other. So what you have at last would only be the two vertical forces in that case, and therefore I would say it will be GO. That means the one of the original G that you experience, and you times it with the sine theta. If I say this is a theta, and of course this is also the theta as well. And after that, eventually you should find the answers at last. By the way, for the unit, you can use Newton per kg, or if you do not use this one, this is still okay if you use meter per second square, because they are exactly the same. Next question is very classic. The question asks you about if there's a satellite orbit on the equator with a period equal to 24 hours. So basically, it moves with the exact point to the Earth. So in that case, there's actually more professional name. It's called the geosynchronous orbit or geosynchronous satellite for these kind of satellites. And if you click into the link, you can find out they mainly, that's what you do for part B. Mainly, the function of this is for transferring the TV and or radio signal, so that for communications. But for the calculation part A is basically this. So you can see it's something about circular motion, of course. So for me, I would prefer to use this equation equal to m r omega square. And for the force, that will be the gravitational force mainly, and for the mass will be cancelled out lately, because that will be the mass of the satellite. And for the omega here, this will be calculated by 2 pi, because it's a completed one circle, right? One cycle, and over the time in second, because well, mainly think about radian per second is the unit for omega. So 2 pi over how many seconds you have will be the omega. After that, you can calculate using the gravitational constant, universal constant, and also the mass of the Earth, which I could find on the Wikipedia. And also at last, you find out the R will be this one. However, pay attention that this R is actually talking about for the Earth from the center to the satellite. The question, in fact, asking you the height of the satellite above the surface. So in fact, you should minus the radius of the Earth. So in that case, you can also refer to Wikipedia. You find out that is the radius of the Earth, and at last you can calculate the height above the surface. Next question is straightforward but slightly painful. For question A, what you're gonna do is you need to write the equation of circular motion. Again, the forces will be the gravitational force, and eventually you can find using the information given, finding out the velocity of the Hubble Space Telescope will be this one. Pay attention to the radius is the height above the Earth's surface, and also the radius of the Earth as well, all together, add together. B is the first part of B is very similar to A as well. So do the same thing again, but this time it said is 500 below its orbit. So the R will be minus 500 here. And at last you should find the answers of this one. Now you should know like why I take so many digits in part A. Normally we don't do it, but for this one, if you don't do it like this, there's no way that you can calculate part B at last, because it asks you to calculate how long would that the space shuttle would take over the telescope. So by taking these two velocity, you can find out the time, which would be the distance over the difference of the velocity. In that case, you should be able to find this like 36,000 seconds, which will be about around 10 hours. Last question is again a very classical question relating the law of gravitation from Newton to a guy called Kepler, and he invented three Kepler's law. And first of all, in part A, what you're trying to do is still you assume right now, assume if you are Newton, you assume you have not figured out the power of the radius here. So what you're trying to do is you try to relate that to the circular motion, which is mv squared over r. And at last, going through all these steps by turning the v into 2 pi r over t, which is the period, at last you'll find the period will be square will equal to this thing. So the thing is, the relationship you build from the Newton's law of gravitation can be like this, together with the circular motion. For part B, Kepler's law, actually, if you try to look at the Wikipedia or anywhere in Google, these three are the Kepler's law. And the last one is that the square of the orbital period of a planet is proportional to the cube of the semi-major axis of this orbit. So simply, what it means is the period square will be proportional to the radius of the circular motion. This is what Kepler, the scientists, physicists, astronomers, find out in the past. He's actually he found out this law based on just the numbers that he observed from the telescope. So he, of course, he is very dedicated to astronomy. At that time, he has no, well, he is not intelligent. Should I say that? He's not. Well, he is very smart, but the equation of Newton's law has not been established. But he managed to look at all the figures, the actual figures for different planets, and he figured out this is the law, the theory that he built. And surprisingly, it's coherent with the Newton's law of gravitation. And eventually, you can fit this in the equation here. And for talking about this question, then the n would of course has to be 2 in that case, because you need to keep this as 3, and therefore n would be 2. That means Newton's law at the first place, this has to be r squared. So please have a try and have a look of the data from the second link I put down here, and you will see all the figures. But for me, I will really appreciate Kepler's work on. I'm pretty sure he's doing trial and error all the times, and he find out this is the golden rule. Thank you for watching. I hope you enjoyed this video. I'll see you next time.